uh, you can get clarification. Otherwise, I will write my own program, and then it may not be uh, in your logic.
Students who have submitted the assignments yesterday, please share your screen to explain the program.
I think Rishi is the one who has raised. Rishi Ahire. He can share that screen so that we can address it.
Sir, may I share the screen
Yes,
from
sir. Sure,
the
sure, sure, sure.
response?
Sure, sure, sir. No
Yes.
problem.
Yeah. Sir, Rohit has submitted these assignments.
Okay.
So, sir, this is the program.
Yeah. So factorial. See in the program. I think Rishi. In the program itself, you have given your input in your R1. Okay. So this R1 is been looped. Okay. So inside your factorial loop. So this factorial. This is known as this program is known as recursive calling function. This is not a normal calling function. It's a recursive calling function. So your output will be present in your A and B registers because you are doing multiplication. So here there is one small thing which you need to address. So here move AB is there, right? So this move AB will not work over here. After mul AB, you have done move AB, isn't it? So if you put this, you will not get your output. So
Yes, sir, actually, there is also one problem in the SJM instruction also.
yeah, see SGM, SGM is a simple jump instruction, okay, uh, which see the factorial loop you are calling uh, here before the factorial loop you have to call the loop actually. So this program has to be rearranged. So I'll just show you. Sir, can you stop sharing so that I can
Yes, sir.
share my screen?
Yes, sir. Yes, sir.
Um, is my screen shared? You can just tell me, sir.
Yes, sir. Sharing.
Okay, okay, fine. Yeah. So now see, whenever we do the this operation, okay, the first thing is you need to start the loop. Okay, so I maximize this. Okay, so now see this org all these things is not required actually. So suppose r naught you are giving 5, R1 you are giving it as 1, okay, then R0 you are moving to R2 for your reference, so just for decrement purpose only. So your R2 is been 4 now. So now what we are doing, so with respect to A and B only it will perform. So first your move R1 comma A. So R1 value was 5. Okay, so R1 value is 1. Okay, so R1 value is 1. It is moved to A. Then multiply 1 with B. So now here B also we have to mention it as, we have to assign it as R to R2. So what we can do is here, sorry, so here first 5 is moved, then 1 is moved to R1, then move I got some small some correction. Let me just start the program once again. I'll start it again. Right. So this is your program. First R0 is initialized with 5, R1 is initialized with 1. So what just you need to do is you need to perform 5 into 4 into 3 into 1. So 5 is in R0, right? So this one you have to consider, and a 1, okay, that will be the least count what we are going to do. So now see here, so decrement R2 you have done, right? So in this decrement R2, your R2 value is uh, 4 now, okay, and R1 value is 1, okay. So 1 has been moved to A register, and then you are multiplying with move AB. So here we have to write one more instruction stating that move R0, sorry, move B comma R2, okay. So now what we are doing, so first R2 value, that is 5 has to be moved. So let us start with R0 itself, okay. So first R0 is moved to B. No. So some logic is missing. So let us first do it in proper way. Okay. So first 5 into 4 into 3 into 2 into 1. So now what we do, so we'll make A as 5, B as 4. So for that what we need to do is, first we'll make this R0 equal to A, then let us make R1 equal to B, then let us store this value in R2, okay. So first what we need to do, so first A has to be moved with as 0 5, okay, or I'll make it as R0, then move R1, or make it as move A comma R0. So with this assignment is done, then decrement R0, okay. So then move those the value to B register, okay. So now this is done. So now A is having 5 and B is having uh, 4, okay. B is having 4. Now what we need to do is we need to start the process, okay. So how we will start is mul AB, So multiplication of AB. So now 5 and 4 is done. So 5 and 4 will get multiplied, okay, and the result will be stored in A register. Okay, so now this value we will move to R0 or R2 comma A. So now what happens? Whatever 20 is there, that 20 is moved to R2. Then what we need to do? We have to decrement the value of uh, so R1. Okay, so when we decrement the value of R1, R1 earlier was 4, now it becomes 3. Then decrement if jump if dj engine. Okay, decrement and jump if not 0. If R1 value is not 0, okay, so what we need to do, or no need of decrement now, here itself we will do it. So using one instruction, dj engine R1. Okay, so decrement and jump is not 0. So if R1 becomes 3 and if it is not 0, right, so what we are doing, you are moving that value. Okay, so one more small instruction we write it, move R1 comma R0. Okay, so here I'll put it as R1 and here R1. So now it will be fine. So this one, okay, so to a loop, let us say it is a loop. Now where this loop should go, so now R1 value is 3. So this 3 has to be multiplied with the previous value. So here we'll put loop. So now what happens? Your 3 is multiplied with 20, okay, and whatever the new result is there, that is moved to 2, okay. Then again you are decrementing R1 by 1 value, okay. So now it becomes 2. So now this tree is completed. Now R1 was 2. Now since it is a non-zero value, the loop executes and 2 into the previous value. So in AB it will have 5 into 4 into 3, isn't it? So then the new value will be there, that we are moving it into R2 register. Okay, then you're decrementing R1 by 1. Okay, so now it became R1 is 1. Okay, so since it is not 0 value, again we are multiplying it by 1. Okay, and you are going to get the result in R2. Okay, then you are decrementing R1. Since it is 0, you are going to come out. So this is a simple program. Okay, so now let us see whether this is working fine properly or not. So let us,
Excuse me, sir.
yes,
Sir, in the program,
yeah.
so the loop will be just before the multiplication instruction or in this instruction?
Directly multiplication instruction we can do it. So this is the simplest way.
No,
Suppose if you are
no, sir.
calling,
Actually,
yeah,
when we are performing the decrement jump not 0 R1,
okay,
the value of the R1 is not moved into the B register, sir.
okay, rightly said, right.
Yes, sir.
Yes,
Yes.
yes, right, yeah. So it has to be moved, right? Exactly. Thank you. Okay, so now I'll just modify that here also. Yeah. So now let us see this. Okay. So R not somewhere R0 I mean. Yeah. So this cannot be done. Uh, so instead of R not, I'll make it as A. Fine. Okay, so now let us see stepwise. So your R naught is 5 and accelerator is accumulator is also 5. Now A we are moving to R1. So R1 is also 5. Next you are decrementing 4. Then R1 is moved to B register. Then first we are performing the multiplication operation in AB. So now it was 14. Now this is moved to R2 register. Okay. Then you are decrementing R1. It became 3. Okay, since it is non-zero, you are going to come back to this, and D is loaded with 3. Then it is moved to 3C. Okay, then C 2 1 multiply and 7 8. So if you see 7 8, so it is hexadecimal equivalent for 120. So 5 into 4 into 3 into 2 into 1 is 120 decimal. So when you convert back to the hexadecimal, it gave 78. So I hope now the program is clear. Students, so now the program is clear.
Yes, sir.
Yeah, yeah. See, someone has used a factorial loop. Okay, so don't use that much of big number there. Okay, just use L1 like that. So any other tasks which you completed and you cannot get the answer, something like that, and stop sharing so that you can share your things. So if no doubts, we can just go ahead with the next part. Okay, so anyone who has done ARM, okay, XM is fine. Now ARM manipulated, anyone, any student has done, they can share it. So just here, I just want to know whether you have learned it or not, or in the process of learning. Nothing wrong in that you are not, you are in the process of learning. But if you are not starting, then it is a concern. Because after spending this much of time, if you are not started working on those things, it will be, it won't be fair, I feel. Right. Then I think no queries from the students.
Students, you are advised to communicate with the sir. Say, the form is open in the chat box also. You can just raise your concern in chat box also. No issues in that. Because say, on Saturday we are ending this internship. So I want to make sure that at least the student runs, writes the program on his home. Say interfacing embedded system, interfacing with working with Arduino, working with Raspberry Pi, everything is fine. Okay, but the basics if you miss, then it will be a problem to you. Fine, then, sir, I think we are not getting any response. We'll start with the next topic. What do you say, sir? Or Yes, sir. Yes, sir.
yeah,
Yes, sir.
fine, fine. Yeah. Right, students. Now we will start our actually in the previous class sessions. I have shared some information regarding the bus protocols. Okay, so but actually, how these bus protocols are used in embedded systems. Okay, so as in the previous session I said, so the transition or the data has to be transferred between the processor and the peripherals
it might be on chip or it can be in off chip. So we require a faster transaction. Okay, so this can be done with the help of parallel communication. But what's the limitation of the parallel communication is the bus width. Okay, so the bus width is the bus width which consumes space in our on the chip or off the chip. It matters, right? So if the size of the data is 64 bit, then we require 64 lines. Okay, 64 wires. In simple terms, if I want to tell, 64 lines you require, and you just imagine 64 lines means what will be the diameter of it. Okay, so that's the main limitation for any bus. So that's why we prefer serial communication, but at a faster rate with a reliable communication. Okay, so that is where this bus protocols came into picture, and with the advancement of this bus protocols, okay, so this embedded system has become robust and compact also. Okay, so that is the reason why we can do all the computer operations with a handheld device called as mobile phone. Okay, so now usually the bus is known as a data bus, address bus, control lines. Anyhow, these buses we have seen already, right? So if you see the uh, classification of buses, so we have the communication bus as serial bus and parallel bus. Parallel bus is the PCI and ISA are the standards what we have. Okay, so nowadays it is faded out almost. Okay, so the serial buses comes I2C SPI UART, and why we use this serial bus is so the processing inside the processor will be parallel, whereas the data streaming will be in serial. So these are used to convert this primarily. Okay, so now so the types of serial buses we have seen something called as inter-integrated circuit I2C. Then we have seen UPI, sorry SPI, that is serial peripheral interface, and UART, universal asynchronous receiver transmitter. And then we are going to see something called as CAN protocol. Okay, so I'll just refreshing this protocol. I2C is an two-wire protocol where SDA and SCL will be there. It is based on completely the master-slave approach. Okay, and then we have SPI protocol which has four wires. Okay, one is uh, multiple output single in. Okay, so then memory in, sorry, master out, slave in. Okay, so master in, slave out, then serial clock, then we have SS, and it is operated in full duplex which is faster than I2C. Okay, so usually this SPI protocol used for between ADCs, that is analog to digital converters, then the memory chips and displays. Now UART, this is a simple UART what you are using for connecting an your projector to a system. Okay, so that is where you find your UART. You call them as RS232, but basically they are UART and USART. Okay, so where we will be having transmission and receiving lines with no clock line. Okay, and it uses some baud rate also. Then we have the CAN protocol, which is mainly used for automations. Okay, so automotive devices. Okay, so this is a multi-master approach. Okay, with priority levels, high priority levels. Okay, then it is very robust and it has inbuilt error checking capability, which makes this protocol on par of the other things. Okay, so usually this CAN protocol is used mainly in your automatic vehicles and industrial automation. Then USB, so the normal USB what you are using, which is a plug and play. Okay, with power and host device architecture, all these things, right? Now, if you try to compare the things, okay, so which is faster is USB is faster, okay. So, but which is reliable is multi-master mode, that is your CAN, okay, and the distance which covers is the CAN protocol. So the distance covered by I2C is very short, USB is medium, and SP and UART, SPI is also short, UART is medium, whereas CAN is the one which can prolong for longer. Okay, so now, right, so now what I will do is I will go with your CAN protocol, CAN bus. Okay, and then I'll take one small case study of industrial usage of your CAN protocol and how the data is streamed, all these things. So let us start with CAN. Okay, so CAN protocol. Okay, so we cannot imagine any embedded system without CAN protocol. Okay, so why? Because CAN is everywhere, and why this is used is it is used for longer distances. Okay, not for shorter distances. So for shorter distances with a higher rate, you can have your SPI, you can have your I2C. Okay, so even you can go for UART. Sometimes you can use your USB also with wires. Okay, but if you want to go for a longer range, suppose say in your industry, your automated devices will be somewhere 5 or 10 kilometers apart. Okay, from there you need to get the information in real time. You need to control it, so you need to monitor it, and then you need to control. So at that time the distance plays a vital role. Okay, so that's why this CAN protocol. Okay, so at the starting it was used in industrial purposes. Nowadays they are used in uh, automation industry. Okay, automotive industry. Why? Because now whatever the vehicle we are getting, everything is in automated mode only. Okay, and for this driverless cars. Okay, so for the driverless cars, your input should be as quick as possible, as how as human reacts, or uh, the reaction time should be greater than humans also. Okay, at that time we require that fast data processing, right? So that's why your CAN protocol will be used everywhere, right? Then this CAN protocol specifies the physical layer and protocol layer, and the message filter layer also we will be having. So then if you see the development of CAN, okay, so this is what we have seen. So now see here, so before the CAN, before the invent of the CAN protocol, okay, so the wiring or the communication within the automation within any vehicle, okay, automotive vehicle used to be like this. Okay, so there used to be a dashboard. Okay, so this dashboard is connected to lightning, power seats, then air conditioning, power windows, power locks, airbags. Okay, and with it has some other mechanical systems which are connected to the dashboard, like anti-lock braking system, then active suspension, then transmission control. Okay, and the engine. Okay, so all are connected in multiple ways. So now if you see the mechanical structure or mechanical things itself, okay, mechanical machines, right? So this anti-lock braking system, okay, will be controlled by a dashboard. Okay, so which in turn will have a communication with the transmission control, then active suspensions as well as engine control. So this many inputs it has to take. Okay, so this is multi in multi out architecture. Okay, so completely your dashboard, lighting, power seats, air conditioners, all these things. Okay, whereas with CAN you can see simple architecture. See this here, the number of lines or more, which makes clumsy. Okay, whereas with the invent of the CAN, there will be only one high speed CAN bus, okay, which is connected to the as a central bus for with your dashboard, and to this CAN bus your anti-lock braking system, engine control, transmission control, active suspension, lighting, power seats, okay, air conditioning, all the or whatnot, all the electrical as well as the mechanical features are getting interfaced or interconnected. Okay, so now what's the basic structure of a CAN? So CAN is of broadcast type, means it will give the data, okay, or it will put the data in the uh, medium. Okay, so whichever the device it requires, they will capture it, just like our radio broadcasting. Okay, so if you take your FM, simply they will pass the information directly. Yes, going. You raise your hand. Find that. So this information will be taken whoever it's request, not inside a room itself you have 10 people, out of 10 all the 10 will not take the uh, will may not be interested in FM. Okay, those who are interested only they will tune to that and they will capture it, just like this can protocol will work.
Okay, so this is a broadcast type. Okay, so all the nodes can can know that there is some data transmission. Okay, and all the nodes invariably pick up all the traffic. Okay, however, whichever is interested, that only will pick up the information. Okay, so we say that it is a multi-master concept. Okay, at the same time, number of nodes are not limited by the protocol. There is no limitation for the number of nodes. Means number of nodes in the sense the receivers. Okay, so and one good thing is here no when it is on broadcast concept, there is no need of having an uh, addressing. Like why we use addressing is to whom we are sending the data, but here that is not required. So that's why it is sent straight away. Then if you see the basic configuration, how the CAN works is there will be a CAN physical bus. Okay, so which will have say some 40 meters of length at the data rate can be okay 1 Mbps, right? So this CAN bus with the help of a transceiver, it will receive the data, and this CAN controller will analyze the data and it will give it to a host controller to a node to the application. So that application can be an ABS application or any other application. ABS is anti-braking system application. Okay. Similarly, at the node AAN also it performs the same thing. Okay. So this is how your CAN protocol is set up. Now, if you see your CAN bus uh, overview, the physical layer uses differential transmission on a twisted pair. Okay, and the bus uses non-return zero bit stuffing. Okay, so these are NZRL. Okay, NRZ stuffing. Okay, so in order to pass the information, then the maximum rate of 1 kilobyte means 1 megabyte per second. Okay, with a bus length of 40 meters or 130 meters, okay, which is uses a twisted wire pair. Okay, is common for a basic CAN. This is a basic CAN what we are sending. Okay, and the message length will be one packet which is equal to 8 bits. Okay, sorry, 8 data bytes. Okay, so 8 data bytes in the sense 8 into 8 64 bits per second or per message can be sent at the rate of 1 Mbps. And the type of security what we have in the basic CAN is a CRC type, cyclic redundancy check type checksum. Okay, so the this bus will handle the serial communication protocols. So with the carrier sense multiple access collision detection. Okay, so can carrier sense multiple access collision detection in the sense. Okay, carrier sense in the sense it will first sense the medium. Okay, so which is free, right? And if it is free, okay, so the data will be captured, and during this process if the same data is being accessed by some other application or some other protocol, okay, there occurs the data collision. Okay, so this collision can be detected. So once the collision is detected, okay, again the CAN protocol what it will do is it will resend the data. Okay, so here collision detection is there, but it is not collision avoidance. Okay, so that is the main concern in the basic CAN bus protocols. So here we see this basic encoding of the data that is done in the physical layer. So it is based on non-return to zero, right? So let us say there is a data string, okay, of 8 bits. So before the 8 bits, you will be having a start bit and you have a stop bit at the end of the 8 bits. Okay, so how the bit stuff relaxes, how the bit stuff is used here. So let us say the original bit stream at the transmitter is 00, 11, 11, 11, 11, and 00. So if you see this bit string, okay, so we'll put a checkpoint. Okay, so for say some for every repetition of the bits, we are going to put an opposite bit. that is what is called as bit stuffing. Okay, so this is non-return to 0 stuff. So let us say here you have so here we have 6 bits. Okay, on the all the status of the 6 bits are ones. Okay, so now let us put a checkpoint as for every 5 bits, or for every repetition of the sixth one, we are going to stuff a 0. Okay, or we are going to stuff a opposite bit, right? Then the new bit stream will be after 5 ones, 1 2 3 4 5. After the fifth bit, okay, the sixth one is replaced with 0. Okay, or we are going to stuff a 0 at the bit. Okay, and then the remaining 2 bits will be processed as such. Okay, so this is how the bit stream will be happening. Suppose the quite opposite also can be done, that is a continuous 0th bits can also be stuffed with an opposite bit. So in the second case, if you see, there are 6 zeros. Okay, so for every sixth zero you are going to stuff a 1. So the origin the converted bit string will be converted as 5 zeros, 0 0, and then 1 bit is stuffed at this location. Okay, that is the opposite status. Okay, so this is how the bits are encoded in uh, the physical layer of your canvas. Okay, so now what are the characteristics of a canvas? Okay, so if you see the canvas characteristics, someone has raised a question. Yeah, so the receiver, how the receiver will know is a synchronization signal will be given between the sender and the receiver once the connection is created. Okay, so I said carrier sense, isn't it? So carrier sense in the sense, suppose say A is the entity which is sending the bit streams. Okay, now B is intended to take that bit stream. Now bit B, sorry, the node B, what it will do is it will send an acknowledgement signal that I am going to take it. Okay, so when it is taking, okay, so then again this sender will send one signal stating that the bit stuffing is performed for every 4 bits or 5 bits. This is called as header information. Okay, so once the receiver, the node B receives that, okay, so when it is receiving the bit stream, okay, whenever there is a consecutive number of zeros or ones, okay, so it understood that for every 5 consecutive ones, okay, there will be a 0, or for every consecutive 5 zeros there will be one bit which is stuck. Okay, so what it will do when it is receiving for every 5 bits, it will see the repetition and it will remove the sixth bit automatically. Okay, so that is what we call that as dominant zeros or dominant ones. Okay, so that is what the characteristic which I am dealing. Okay, so as soon as the, I think I'm clear now. Okay, so now as soon as one node transmits a dominant 0, okay, will be sent, okay, or a dominant uh, recursive dominant zeros or dominant 1 will be sent. So this dominant 1 is said to be recessive 1. Okay, recessive 1. Okay, so as soon as one node transmit a dominant 0, the bus is in dominant state in the sense, so it will be passive all the time. Okay, so whenever the recessive bits are sent, okay, the bus is in recessive state which is always high. Okay, so only if all nodes will transmit. So dominant 0 will be such like that the uh, master will be sending the data stream. Okay, and the recessive bits will be used when master receives the data from the nodes. Okay, so let us see here, there are 3 entities and this is the bus. Okay, so in the first case it is dominant D. So A will be D, B will be D, C will be D. In the sense, the bus will is reserves the ability to transmit the data to A, B, C. Now in the second case, even though the bus is in dominant, Your C is in R, recessive state. So recessive state means your bus can transmit the data to A and B, whereas it can C can transmit the data to the bus through the bus to the master. That's why it is reserved as R. In the next case, B is having the recessive bits, so meaning that B intends to transmit the data to the master. Okay, so like this, R and C will be done. So check the last case where bus is in R. Okay, so when this case occurs is when all the nodes in the connected to the central system or the CAN bus intends to send the data to the master, then your bus automatically changes from dominant mode to recessive mode. Right. So now this is the actual structure, internal structure, where you will be having the recessive state and dominant low state. Okay, so if you see your recessive state, that is very high, the CAN single logic bus line, it is called as. Okay, the CAN bus is connected to a 5 volts DC. So this is acting as an 1. Okay, so active 1 to the transmitter. Okay, so transistor. So if you see the transistor, so this will be low here. Okay, so here low means your transistor is in your off condition, so your CAN bus will be in your recessive high state. Okay, whereas if you see your dominant low, okay, so here it is a mixture of dominant low, right? So dominant low, so your transistor is going to be your base of the transistor will be 1. Okay, so when your 5 volts is acting as a VCC to this transmitter, okay, sorry, transistor, this transistor will be in on condition. Okay, so this whatever the 5 volts you are going to give, this 5 volts is going to go to the ground through the transistor, so here the state will be 0. Okay, so that's why it is called your node A will be in your dominant 0 mode. Okay, so recessive mode, since the transistor is in off condition, the no current is going to pass through this transistor, so your state will be high here completely. Okay, so this, what is this R and T? So R and T here known to be the receiver and transmitter, whether the node is acting as a receiver or whether the node is acting as a transmitter. Right. So this is bus access and arbitration. Okay. So like CSMA CD, that is carrier sense multiple access collision division by non-destructive abstraction. So non-destructive abstraction in the sense, so even though the collision is detected, okay, the data should not be lost. Okay, and there should not be any cut off flow data. So usually the bus transmission speed, okay, so what are the transmission speed we are going to have? So that maximum speed is given as 2 into TPD, which TPD is the propagation delay of the electrical medium. Okay, so as the CAN bus length, which is in meters, as it is increasing, so the bit rate is going to come down. Okay, so the shorter the CAN bus, the larger the bit rate will be. So this is with respect to twisted pair only. Okay, so if you use an optical cable, that will be a different scenario. Okay, so if the CAN bus is of made of twisted pair in the sense, if you see the LAN wires, okay, not LAN wires, if you see the coaxial cables, okay, so they come in twisted pairs. Okay, so where there will be high, low, and neutral. All three are twisted in a copper wire. Okay, and it will be having a series. So nowadays most of them are not using this twisted pair. Okay, so the speed of the nature of the CAN bus is converted to an optical nature. Okay. So if you see the CAN protocol, okay, so this specifies small packets of data that can be that may be transported from point A to point B using a shared communication medium. Okay, so usually it has a flow control, means how the data has to be flowed with variable speed. Okay, when it has to stop, when it has to restart. Okay, if collision is happening, what has to be done? That is what the flow control is. Okay, then the transportation of data larger than the can fit in 8-byte message. So whatever the message it is there, it has to be uh, um, packetized into 8-byte message, means 64-bit message. Then if required, we have to use the node addresses. Okay, so usually CAN protocol basically doesn't require the addresses, but still the advancements in the CAN protocols, okay, is providing the node addresses also. Then establishment of the communication, etc. So these are the main features what it has to look. Then if you see the higher layer protocols, okay, so higher layer protocols are used in order to start up the procedure into the bitrate setting, distribute the addresses among the participant nodes or kinds of messages, okay, and determine the layout of the message. Okay, some other will provide the device net, CAN kingdom, right? CAN open. So these are some higher end protocols which are used in application layer. Now coming to the CAN standard. Okay, so the CAN standard message is defined in 4 messages. Okay, one is the data frame. Okay, then remote frame. Next one will be the error frame, and then overload frame. Okay, so the messages uses a clever scheme of bit stream. Okay, arbitration, right? And CAN standard also defines the elaborated scheme for error handling and refinement. Okay, so this can may be implemented using different layers, and there are also a number of different connector types which are being used. Okay, so now let us go with the data frame itself straight away. So this is the CAN data frame what we have. Okay, so this is CAN 2.0 A standard. Okay, and this is CAN 2.0 B standard. Okay, so CAN 2.8 standard has 11 bits ID. Okay, so whereas our extended CAN will have a 29-bit ID data frame. Okay, so what is this 11-bit ID data frame? Okay, so your identifier is it starting of the frame. Okay, so you will be having a data field where you will have a control field which is prefixed, and you will be having a CRC field as a suffix. So what is this CRC field? So cyclic redundancy field, which will check the errors that are occurring during the transmission in the data path. Okay, so in this data field, okay, so whatever the data you are sending, that is 64 bit data. Okay, so this 64-bit data, if there is any malfunctioning or if there is any change in the data frame, so that will be detected. Okay, and it will be uh, sometimes it will be corrected also. Okay, so using this CRC field. Now before that, you will be having an arbitration field. Before the control field, you will be having an arbitration field. We call them as reserved field for identifier. Okay, so this reserved field for identifier in the sense, it is reserved to identify the receiver. Okay, then we will have an acknowledgement slot. Okay, so sometimes this slot can be used for CRC delimiter or acknowledgement delimiter. Okay, so acknowledgement delimiter in the sense that this complete frame or the packet of data is transmitted successfully, it is going to have a acknowledgement. This data packet is returned back uh, to the sender with an acknowledgement. That is acknowledgement delimiter. For suppose in this data feed, if there is any error is occurred and which cannot be corrected, then using this CRC delimiter, okay, this status will be sent back to the sender, okay, stating that the data has been corrected, so that the sender will retransmit this data again. Okay, so this is will be the starting of the data frame, and this will be the ending of the data frame. Now this is your CAN 2.A standard. Okay, whereas CAN 2.B standard, you will have two identifiers.
Okay, means if the data is intended to be sent to more than two receivers at a time, okay, so you can have uh, all the identifier fields which can be stored in the arbitration field. Okay, so that's the reason this 2.b has an higher data frame size when compared to the 2.a standard. Okay, the rest of the fields are same. The only difference is here you will be having only one identifier. Here you have two identifiers which separates like start of the frame and uh, end of the frames. Okay, next, if the next thing is the remote frame. Okay, so this remote frame, okay, so remote frame is just like a data frame with the two important difference. So what is that is a remote frame uh, is marked as, so the explicitly it is marked as a remote frame. Okay, and there is no data field in this remote frame. Okay, whereas in your data frame you will have your remote frame, okay, with arbitration, right, but it will have some data, whereas in your remote frame there won't be any data. So now this is a simple remote frame, so which is used for referring that what is the data length it is being transmitted every time, okay, or any other information related to the data. Okay, so you will have the start of the frame, you will be having the end of the frame, then a control field, and for this control field also you will have a CRC field with acknowledgement slot. Okay, so earlier you have the acknowledgement delimiter for CRC as well as data. Okay, whereas here the acknowledgement will be for your control field and your CRC field. So most of the time this remote frames will be emptily sent because there won't be much controlling, okay, required. Suppose it is an is a, let us take an example in an car, okay, in an automatic car. Okay, so if you are just putting a button to close the window, okay, so it doesn't require any feedback or anything. So once you press the window it goes on, okay, and it get closes, right. For suppose if any obstacle came during the closing, right, it has to stop, right, otherwise what happens, it also get, the obstacle will also be pushed up, okay, and if, so for suppose if it is a human hand or anything, it will get damaged, right. So at that time we require an uh, uh, feedback, isn't it? So here the control field will use that feedback. Okay, so whenever there is an uh, obstacle, okay, so the moving the pushing up of the window should be stopped. Okay, so that's why this remote frame is used. So sometimes it will be empty. So nowadays whichever the automatic cars we are getting, so everything we have a feedback. Okay, it means the control field is used, so the remote frames are used. Okay, so there are semi automated vehicles where this remote frames will be empty most of the time, and again from application to application it will change. Okay, like the side window moving, okay, or the camera operation, the dashboard camera operations, like this. Next is the error frame. Okay, so error frame is what type of at the initial stage in the using the CRC check itself we are doing the fixing the errors. Okay, whereas sometimes uh, there might be an errors which cannot be corrected using CRC. At that time, this what type of error, that error type need to be given to the sender, right? So for that we use this can will use an error frame. Okay. So now let us say let us take an condition where the error frame consists there is an error, error frame has been received. Okay. So this error frame, how does it look like? This error frame will have 6 bits of same values, okay, so violating the bit stuffing rule, right, and an error delimiter which is an 8 recessive bits. Recessive bits means ones. Okay, so the error delimiter provides some space in which the other nodes on the bus can send the error flags when they detect the first error flag. So this will be the error flags, okay, followed by your 6 bits of the same value,
okay, and an error delimiter. Okay, so this error flags whatever here showing. So if a receiver receives an error data, so that will be flagged in this error flag, okay, and it is sent. Then we have an overload frame. Okay, so this overload frame is just for the completeness, whether the data has been transmitted successfully or not. Okay, if you have an error, okay, then only we will receive, or then only we are going to send. In the same fashion, okay, when the data is received successfully, then only this overload frame will come and says that the data has been completed, data transmission has been completed fully. Now this is an implementation of an CAN bus, the using in the OSI physical layer, so which has CAN transmitted data, CAN received data. Okay, and if it is an optical transmitter receiver, okay, so both will be binded in an optical fiber. And if it is a twisted pair, okay, so both the wires are twisted and it is used between the two ends. Okay, so say this in the twisted pair we will be having two buses. One is CAN bus high, CAN bus low. Okay, so these two buses are driven by the nodes at the different signals. Okay, so the impedance that is maintained for this twisted pair will be of 120 ohms. So whenever this 120 ohms is uh, varied, okay, so then there comes a condition called the impedance mismatch. Then what is the influence of EMI on the CAN? If you are using twisted pair only. If you are not, if you are using a fiber optic, there won't be any EMI. EMI will be zero for fiber optic. Okay. So whereas if it is a twisted pair, okay. So how the EMI will influence? Of course, the EMI will influence it. Okay. So whenever that influence is directly impacted on the impedance of the twisted pair. So if at all if this 120 ohm is not maintained, then we can say that it is under some EMI, and immediately the respective action need to be taken on it. Now coming to the standardization, so we have three standardization of the CAN. Okay, so class A, class B, class C. So class A will be the maximum rate will be up to 10 kilobits per second. Okay, class B also is up to 10 kilobits to 125 kilobits. Okay, uh, so this is for low bus speed. Okay, then for class C, the high speed bus applications, which rates from 125 kilobits per second to 1 Mbps. So it is used for real-time applications like engine management, gearboxes, ABSs. Okay, so in the same one automatic car itself, you can have three classes of uh, CAN buses. Okay, so one for the real-time, one for dashboards and diagnosis, and one for some control applications. Then the bus levels in the sense the voltage ratings, what are maintained. Okay, so usually the voltage rate will be 2.5. Okay, for the recessive one, and for the dominant zeros, it will be 1.5 volts or 3.5 volts. So the difference should be maintained at 2.5. Okay, so now this is the simple, we call them as a basic structure, but in the industrial terminology it is called as a chip CAN controller. Okay, this bus controller will have a processor again. Okay, so which will have a CAN bus protocol controller. Okay, so it is connected, just like your ALU, it is a CPC, we call it as CAN protocol controller, right? Which has some registers. Then we have some buffers, transmit buffers and receive buffers, and some host interfaces. Okay, so the host interfaces which will have the transmission and receiving lines usually. The this is the full CAN controller architecture. Okay, so the hardware messages filters, sorts and filters a message without interrupting the CPU. Okay, CPU here in the sense your CAN protocol controller itself. So you have status and control registers. Instead of having a transmitter buffer and receiver buffer, we have only the receiver buffers, and we have certain blocks called as message objects. Okay, so it will take the information from the message objects, and which is required for that controller only, which is required for that application, that only will be accepted. Okay, remaining are filtered out, and it is sent back to the receiver buffers. Okay, so this is an Caterpillar 979 system where the CAN is used. Okay, so if you see the darker line, okay, this is an CAN data link, whereas dotted line is a CAN CA data link. Okay, so we have this CAN bus is connected to 195 sensors and actuators. Okay, with wireless data link. It's not a wired data link; it's a wireless data link. So inside the braking and cooling system itself, we have this many input components and output components, and for monitoring, we have the again input components and output components. If you see the input components, you have a test switch, you have rear gear wheel speed sensor, okay, uh, left rear wheel, right rear wheel, okay, auto rotor on off, okay. So brake cooling pump speed, radiator fan speed, brake oil filter. So many inputs are there here. So all these inputs, okay, is used to just control your braking or cooling control. And this is one transmission control. Okay, so how the sensors data is collected from the sensors, and how it is getting actuated. Then we have chassis control separately. Okay, so all this chassis control is controlled with the help of some input components. Okay, and these are some standard SES standard workload. Ma'am, yes madam, yes ma'am. Yeah, I'll be there. Uh, yeah. So there was a doubt like if EMI source affects both CAN high and CAN low equally, why does the receiver still read the correct data? So if the EMI source affects both CHA, H and L equally, it will never affect it. Okay, if it affects, the CAN bus is failed. Okay, the receiver will receive the data will be of a garbage value, or it will be of unwanted values. Right. I think I have addressed this answer. Okay. Uh, one. Yeah. So we'll have some 5 to 10 minutes break, and later we'll come and we'll take one industrial standard CAN protocol implementation, and we'll see that today. So is that fine, sir? Saurav sir?
Yes, sir.
Yeah, fine. So after
Yes, sir.
5 minutes, I'll be back.
Yeah, right, sir.
Yes, sir, going well. No, yes, sir, going well. No problem.
Okay.
Yeah. Students, if you have any query based on this current discussions, current topic, because it's very important, CAN protocol implementation. Okay. If you have any problems, you can have a discussion. Nikhil,
Yes, sir.
तृप्ती, अं, आता हा टॉपिक खूप महत्त्वाचा आहे कॅनचा.
Yes, sir.
आणि त्याचं प्रॅक्टिकली इम्प्लिमेंटेशन जे आहे कुठल्याही व्हेकल्सला हे फार म्हणजे तसं क्रिटिकल आहे, कारण ECU जो आहे हा त्याशिवाय बनतच नाही. तर सर्वांना महत्त्वाचं आहे की हा कळून घेतला पाहिजे. याच्यात काही अडचण असेल, क्युरी असेल तर विचारा, डाऊट असेल तर. आणि याच्यावर तुम्हाला डीपमध्ये जाऊन परत एकदा अभ्यास करावा लागेल. पण हा प्रोटोकॉल जर येत असेल, तर जो एम्बेडेड डिझायनर ज्या डोमेनमध्ये जायची इच्छा आहे, ऑटोमोटिव्ह सेक्टरला खूप रिक्वायरमेंट आहे एम्बेडेड मॅनेजर्सची, इंजिनियर्सची. आणि मोस्टली एम-एन-सी कंपनीज ज्या आहेत, या सगळ्यांचे प्रोजेक्ट आता ई व्हेकलवर चालू आहेत, ऑलमोस्ट ऑल. Getting it? So
Yes, sir.
everywhere, this particular thing is very important as a designer point of view to understand.
Yes.
आपण बऱ्याच वेळेस आहे ना हा प्रोटोकॉल प्रोजेक्ट्समध्ये इम्प्लिमेंट करण्याचा प्रयत्न केला. आज नाही, 2015-16च्या बॅचपासून जो विकी चौधरी आहे, जो चायनामध्ये आहे, जो इथे R&Dमध्ये होता रिषभला, लक्षात घ्या, 17-18चा पास आउट, त्याच्या बॅचपासून आपण कॅनवर वर्क करायचा प्रयत्न करतोय. हे बाकी स्टुडंट ऐका मी जे सांगतोय, बट वी डू नॉट गेट इन अ प्रॉपर वे. Okay, so let's see if anyone is going for automotive sector any project in the final year, and if he is going to work on the CAD interface protocol, then it will be a good project. In that case, whatever the guidance is required from the industry or any particular expertise like that, we can take it. We have the resources, we have the network and contact, no issue, along with the academy and industry also. त्यामुळे याचा विचार करा. त्यामुळे लर्न करताना क्युरी असेल ते विचारा. आणि आफ्टर द सेशन पर डे तुम्ही तुमची प्रॅक्टिस चालू करा. या टॉपिक्सवर रीड आउट करा, नोट्स काढा, सर्च करा, असाइनमेंट दिलेल्या सगळ्यांनी सॉल्व करा. सर्टिफिकेट ज्यांना पाहिजे त्यांना डेफिनेटली करायचंच आहे. कोणालाही याच्यातनं वे आउट नाही आहे. मग तो थर्ड इयरचा कॅन्डिडेट असेल किंवा बीचा कॅन्डिडेट असेल, इंटरेस्ट घेऊन करा. ठीक आहे ना गोविंद? गोविंदची काहीतरी क्युरी आहे. ठीक आहे, जेव्हा एक्सपर्ट येतील ऑनलाईन त्यावेळेस डिस्कस करा. जान्हवी, जान्हवी, आर यू इन फायनल इयर और थर्ड इयर?
थर्ड इयर सर.
ओके, कळतंय का काय चालू आहे कंटेंट?
येस सर.
फर्स्ट दिवसापासून तू जर जॉईंट असेल आणि थोडा अभ्यास पण जर करत असेल, उरलेल्या वेळामध्ये स्टडी करत असेल या टॉपिक्सवर, तर डेफिनेटली लिंक लागेल. नसेल तरी सुरू करा. दिस इज व्हेरी गुड स्टार्ट फॉर यू पीपल ॲज अ थर्ड इयर. आपण थर्ड इयर मिनी प्रोजेक्ट सगळे STM32वर मोस्टली आणि ESP32, बरोबर आहे निखिल?
Yes, sir.
म्हणजे फार कमी जणांचा आर्डिनो चुकूनच एखाद्याने केला असेल, पण शक्यतो STM आणि ESP याच्यावरच आपण
Yes.
केलं. लक्षात घ्या का बरं आपण केलंय. जेव्हा कालचे जे स्पीकर होती अंकिता, जी इंडस्ट्रीमध्ये काम करते एम्बेडेड सॉफ्टवेअरमध्ये, ती STMवर काम करते.
Yes, sir.
कारण इंडस्ट्रीमध्ये आर्डिनो आणि रास्पबेरी पाय नसतो चालत. तो प्रोटोटायपिंग पार्ट आहे, पण रिअल प्रोडक्ट डिझाईनमध्ये नसतो तो. तर या सगळ्याचा रेफरन्स घेऊन आपण मिनी प्रोजेक्ट करताना मुलांना पुशअप करतो की नाही याच्यावरच काम करा. त्याच्यामागे रिझन्स असतात. ठीक आहे, नो प्रॉब्लेम, कॅरी ऑन.
I think we can start now.
Yes, sir.
So, any students have some any doubts? The forum is open. So, what's the role of CRC play in CAN communication? So, CRC is a cyclic redundancy check. Okay, so it is the simplest method to detect the error in the data stream. So, for suppose, yeah. So, is my screen visible? Please confirm.
Yes, sir. Visible.
Oh. See, whenever you just send a data stream like this randomly, okay, so this will be a random data stream that will be sent. So let us say after the stuffing also, you are you after during the data transmission, it has been converted like this. One, one. Okay, so now if you see the first second bit, okay, so this has been modified. Now, what this CRC checksum? CRC checksum in the sense there will be an arbitrary number, okay, like 1 or something like this, okay, so which will have, okay, so this is known to be the checksum. When it is divided, when this data string gets divided by this, you will get some random numbers, okay, 000 like this, okay. So when the receiver sees this data string and your checksum, the division should be exactly the same thing, okay. So whenever it doesn't receive this when the error is occurring, definitely this number will change. This is just an example, arbitrary examples I'm doing, okay. So there is a map which is involved here, okay, where we will be dividing the message signal by the checksum, okay, and whatever the remainder you are going to get, based on the remainder or the quotient, we are going to decide which bit has been errorized, okay. So now this might be the quotient what we are receiving. So now see here, these both are not matched, okay. So when these both are not matched, okay, the thing is the error has been raised. So the receiver will see that the error message it has received, and again it will acknowledge, okay, to the sender that stating that it has received the error message through the error frame, okay. So for that only your CRC checksum will be used. Yes, cyclic redundancy check. Okay, then we'll go to the move to the next technology. So this is called as Copper Hill Technologies. Okay, so which is exactly used for an automated cars, right? So hope my screen is visible now.
Yes, sir.
Yeah. So this is a reference which I have we have taken. Why? Because it finds the implementation of this CAN protocol in automotive industry, right? So this everything we have done. So now this Copper Hill Technologies, okay, so has developed a CAN, okay, which is called as a serial network technology, okay. So it was actually originally designed by the Bosch for the automotive industry. Then it became very popular in industrial also. It is a reverse way. So usually CAN was developed for CAN protocol was developed for industrial, okay, which has been implemented for automotive industry. But this serial network technology, okay, so it's been first concentrated on automotive industry, which became popular for industrial automation, okay. Then this network technology is established using the microcontrollers. So and it is suited for real-time applications, okay. And it this
they have replaced this dual port RAM technology. Instead of a single port RAM technology, they have a dual port RAM technology. Okay, and the data rate is up to 1 megabits per second, and the message is the same thing, and they have standardized it into ISO 11898. Okay, so this is will be the CAN history. Okay, so how the CAN has been first started. Okay, then how it has been done, how the serial bus technology has converted to a CAN. Right. So now see here, the number of nodes that a CAN can handle is in 2007 it was 600, but in 2025 it is two zeros extra. Okay, so two zeros extra means it will 60k. Okay, 60k nodes it can handle. No, maybe more than that also. If you see the Tesla car, right? So it is implemented with CAN3 protocol. Okay, uh, with having more than 1 billion nodes. Okay, so each and everything is a node in Tesla car, right? Even right from the mirror, okay, right from the seating, right from the steering, okay, right from the horn also. Okay, everything is considered as a node which is controlled by a canvas. Okay, so if you see the other applications of the CAN, we can have the buses, semiconductor industry also nowadays they are doing this usually for handling the wafers. Okay, as usual in robotics we have. Then in aerospace now slowly they are implementing this CAN protocol nowadays. Okay, in aerospace applications. Then in some building technologies, medical equipment also they invented this for real-time scanning. So the only real-time scanning what we had was ultrasonic earlier. Now this ultrasonic has improvised as 2D, 3D. Okay, and they are recreating it, and especially in augmented reality. Augmented reality combined with the medical field. Okay, so they are just showing the organs which are inside the human body to the outside world. Okay, without using any scanner, without using anything, right? So with the help of this CAN wireless protocols they are. Okay, so these are some advancements in CAN. Okay, so then CAN CIA, that is CAN in automation. Okay, so this in this if you want to become an CIA member, okay, there is not a CIA which is governed by USA. Okay, so CIA means CAN in automation. Thus it is. Okay, so you can become a member at any time. Okay, so using through this portal, so there you can network with the industrial manufacturers, top industrial manufacturers. Okay, and how they do the how they're modifying the CAN protocol based on the application. Okay, and they are ready to they are open up to accept any protocols developed by any student or any faculty, anyone. Okay, so that is a good platform. Those who are interested in, especially CAN. Okay, CAN embedded system. CAN is one part. Okay, so which controls the complete embedded system. So without CAN, you can't imagine any automation nowadays. Okay, so the main characteristics we have seen that multi-master bus, message broadcasting, message priority, then limited data links, then 1 megabit per second data rate, excellent error detection and fault confinement also. Okay, so now the implementation of the CAN. So usually we have an physical layer, data link layer, network layer, transport layer, session layer, and presentation layer. Okay, in any normal network. Whereas for the CAN, all this network transportation, session, and presentation layers are combined together. Okay, so we call them as high layer protocols. So only four layers will be there for us. Okay, physical layer, a data link layer, then higher layer protocols, and application layer. So with what the main benefit is, this physical and data link layer are implemented on silicon. Okay, and all the processings will be done here only. So some maybe wonder that this edge computing, what we call, right? This edge computing has started in CAN protocol first and first without knowing. So until they have been named by someone, because all the processing, okay, error detection, everything was done in these two layers only, the physical layer and the data link layer. Okay,
So since the processing is done at the device end itself, it is called as edge computing. Okay, so the software development engineer is not involved actually in writing the protocol features or anything. So it is a low cost implementation. And see the data frames we have seen, the remote frames. So the actual structure, how the Copperhead Technologies has implemented this thing, they have modified. See, earlier we had only acknowledgement field, CRC field, data field, control field, and arbitration field. Okay, so this arbitration field we called as an identifiers. Okay, so now they have added end of the frame one and IFS field also. Okay, and bus ideal fields also they have added, so that this scan will be more secure. And for the remote frame, okay, so they have added the same as end of frame and field, start of the frame, end of the frame, and after that IFS. Okay, then for the error frame, okay, they have reserved or they have increased the flags, 6 bits flags which have been which is dedicated design, it has been increased to up to 20 bits. Okay, and the interframe space they have given for 3 bits if any extra bits are there, and the error delimiter earlier was 6 bits, but they have implemented using 8 bits. Okay, then the overload frame is a special error frame. Okay, so when it is required, then only we are going to do it. So the transmission request, remote transmission request. Okay, so how the data frame will be there is, so you will be having a 11-bit identifier, then we have an RTR, that is remote transmission request, then followed by control field, data field. So whenever this RTR is 0, okay, so it will broadcast the message to the canvas. Then the remote frame, in the remote frame your RTR, that is remote transmission request, will be 1, okay, stating that it is not a data frame, it is a control field. Then the message broadcast in the data frames they have fixed as so let us say 4 nodes are there. Okay, node A, node B, node C, and node D. So you have an application message buffer, and this is a CAN bus. So you have a message filter, right? So when node A transmits a message, so without any message filter, it is transmitted. When node B, C, D receive the message, okay, so it is received through the message filter, right? So let us say in this BCD only B and C receive the message, okay, and node C declines. So at the message filter itself it is stopped. Okay, so that's why here you have a tick mark. Here you won't since C is not since he declines. Okay, so this application layer will send a decline request or decline message to the message buffer, to the message filter, so that the message will not be taken back to the application. Then message how these frames are received. So Node.js sends a remote frame request. Okay, so it requests the frame. BCD receive the message. Okay, only D accepts because B and C declines the message. This is the method of requesting. This is the method of broadcasting. Okay, so for broadcasting or requesting, the node A, which is said to be the center node, which will send the request or send the data. Then in the second case, okay, so A and B, so once the message request is sent, the this B accepts, okay, B and C declines. Okay, so in the second case, the A and BC, ABC receive the request messages, which is sent by the node D, okay, and AB accepts the request and C declines. Okay, so whenever there is a decline, the message will not pass to the application layer. That is what we need to understand. So here in this scenario, okay, all the 4 nodes, okay, are allowed to send the data, are allowed to receive the data. But at any time, only one node can act as a master. Okay, and the remaining nodes will be a receivers. Okay, or we can call them as slaves. So as per that, the data frame, remote frame, and overload frames are framed. And see here, this error or overload frame. So whenever an error frame occurs, okay, then there will be an retransmission. So this is the retransmission frame. Okay, retransmission request will be sent, and again the same data frame will be resent. Okay, so now if you see the message format size, how much size the frame format is there. So the start of the frame, 1 bit is reserved. So the message identifier 11 bits, RTR 1 bit. Totally here itself we have 12 bits. Then control bits we have 6 bits reserved, and the data field is maximum 64, and the CRC sequence checksum is 15 bits. Okay, then we have 1 bit which is uh, empty bit. Then we have an acknowledgement 1 bit and the delimiter bit again 1. Then end of frame signal, end of frame field we have 7 bits. Then IFS, that is interframe space, we have 3. So totally if you add everything, so the bit stuffing will be done right from the starting of the frame to the CRC sequence. Okay, and the acknowledgement field is reserved from the first delimiter to the end of the frame. All right, so the complete CAN data frame consists of bit stuffed field as well as acknowledgement field, where the size of the acknowledgement is 10 bits and the size of the bit stuffing is 12, 8, 16 plus 64, totally 70, 80, 80 plus 15, 95 bits. Okay, so 95 plus 10, so 105 bits will be a simple message frame format. Okay, so if we want, then there is an extended protocol. Okay, so which has a standard message identifier is modified from 11 bits to 29 bits. Okay, so so both formats, standard and extended, may coexist on the same campus. Okay, so this CAN protocol may have the actual data frame as well as the extended data frame on the same line itself. Okay, so the distinction between the main both the frame formats is managed by the a bit called as IDE, called as identifier extension bit. Okay, so it comes where it comes at the control field. So then we have seen the dominant and recessive bus levels. So both are operated at the same fashion in this Cooper relay. Then arbitration principle. So arbitration phase. So how the bus arbitration will be done? So first is start of the frame will be sent. Okay, so that will be the first bit. Okay, so whenever see at the first fifth bit, okay, in the receiving mode it is low, and for the node B it is high, since uh, it is not it is declined. Okay, and the C is accepted. Okay, node C is in ideal position or in receiving mode completely, and in the bus, okay, the state of node A will be uh, reflected in an opposite with an opposite state. Okay, if it is with respect to node C, okay, it would have been high. So this is how the arbitration phase will be changed. Okay, so now how they are worked. Okay, so first it will wait for the intermission field. Okay, so intermission field specifies that the one data frame has been set and the new data frame is going to be received. So first it will transmit the SOS, the start of the frame, then transmit the next arbitration bit. So if the next arbitration bit is equal to the bus level, okay, whether it is high or low, if it is high, all the arbitration bits are transmitted. Okay, if they are transmitted, all the bits are transmitted, the transmit reset of the message will be done. For suppose if all the arbitration bits are not transmitted, it will wait for the next bit, next arbitration bit. Okay, and if at all, if arbitration bit level is not equal to the bus level, then a dominant bit is transmitted. Okay, then it will switch to the receiving mode, and again it will wait for the intermission field. Okay, if the dominant bit is not transmitted, then the error status will be
sent out. If it is not receiving, then it will switch to the receiving mode. Okay, so that whenever it is moving to the receiving mode, the meaning is it has lost the arbitration. So if it lost the arbitration, the data is not sent or transmitted successfully. Then the main rules, so we have to follow certain main rules, okay, or the Copperhill technologies has framed certain protocols, okay, for bus arbitration. So bus is considered ideal after transmitted message plus intermission field, okay. So that's the first protocol. Then the node that transmits a message with the lowest id, or we can consider as highest priority, wins the arbitration and continues to transmit. Okay, competing nodes switch to the receiving. So the meaning is only one node will be transmitted at a time. Then the nodes that lost the arbitration will start a new arbitration as soon as the bus is free for access again. So no message gets lost in this process. Then data transfer and synchronization. So here we have two, this Copperhill Technologies has implemented two methods. One is Manchester encoding method, and other is NZR. NZR in the sense bit stuffing. For every 6 or 5 consecutive bits, the opposite bit will be stuffed in the next place. Okay, the Manchester encoding, it follows some math. Okay, so which will convert the bit stream into Manchester coding, and then the bit stream is going to be sent. Okay, then one thing we have to be very sure is whenever a data frame is sent, okay, so the starting of the frame and ending of the frame has to be defined properly, and all the, you should have a constant bit level over the same bit type. Then there is a second method of synchronization. So the sender sends the complementary bit after 5 successive bits of the same polarity. So receiver filters the complementary bit. So that is bit stuffing method. Okay. Then we have the third synchronization method. Okay. So provides additional signal edges for data synchronization. So whether it can be a falling edge or a level stuffing. Okay. So see, the bit stuff has to be considered when it is rising or when it is falling or when it is at the level tree. So this additional feature we can have for synchronization. So further synchronization we can do with a programmable phase buffer and the resynchronization jump bits. Sorry. So the bit stuff range as shown in the earlier case, the same thing. The checksum applied till the bit bit. So after the checksum is added, it is called as bit stuff frame. Until the end of the frame, we call that as scan data frame. Right. So the frame length due to the bit stuffing, so the whenever we do the bit stuffing, the frame length is going to vary. So if the data field is having 0 bytes, so no bit stuffing, it will be usually 47 bits. If you are using 8 bytes, the maximum bytes, if you are using, there will be 111 bits. So maximum bit stuffing if you are doing at the worst case, so in the data with the 0 bytes of data, it will be 55 bits, whereas with 8 byte data field, it will be 135. So the average bit stuffing will be 49 bits, and with minimum data bit bytes, whereas with the maximum data bytes, it will be 114 bits. Okay, so it is based on this math is based on 11-bit identifier. If you go for a 29-bit identifier, then this will be increased. This 147 will get increased. Okay, and this 1111 also will get increased with no bit stuffing as well as managing bit stuffing. Then a bit monitoring. Okay, so when exactly does a receiving can know read the bit information? When does it exactly reach? Okay, so usually if you are having a bit rate of 1000 kilobits per second, then the nominal bit rate will be 1.
Okay, so 1 microsecond means 1 divided by bit rate is equal to normal nominal bit time it is. Okay, if it is 500, 1 by 500, it will be 2. Okay, so this is how the relation we can say. So the nominal bit rate, okay, will be is given by 1 by the bit rate. Now the second bit monitoring, the partition of CAN bit in time into 4 segments. Okay, so the 4 segments are synchronization edge sequence, then propagation sequence, then phase sequence, and resynchronization jump bit. Okay, so what is the synchronization sequence? Okay, so signal edge is expected here, whether it can be a falling edge or rising edge. Okay, so any deviations will affect the phase buffer. Okay, so that is how we are monitoring the using synchronization sequence, then segment or signal. Okay, then propagation signal, so it compensates for signal propagation times within the network, and we have the phase segmentation 1 and 2, so which is used for again with signal edge phase errors by adjusting their lengths. So the resynchronization of jump width uh, defines the upper limit to adjust the phase buffer length. Then there is one method called as hard synchronization. Okay, so this is done at the starting of the frame, so which will reset the internal timings of the receiving node. Okay, so this synchronization, so TA outputs until TA output is generated. Okay, so the bus line will not get activated. Okay, so once the bus line is activated, then TB input is going to be taken. So this is what is called as synchronization. So usually at node A, once the node A completes the data transmission, so the synchronization signal has to be sent for the next frame to be received or next node to be uh, received. Okay, so there will be a transition or a synchronization between node A and node B. Okay, until TB input means the transition time input for node B is accessed. So then we have a bit synchronization within the frame. Okay, so how the bits will be sent. So the phase signal 1, phase segment 2 correct the positions of the bit sample point according to the phasor. So if this is the received bit level, it has to be synchronized with the bit timing pulse. So it has to start at the middle. If it is starting at the middle, the bit level has to end at the middle only. Suppose it is starting at this point. Okay, then the phase 2 also should start at this level only. This is how the bit synchronization can be achieved. Then the phase errors, the received bit is at this timing. Okay, which is supposed to get at uh, sync starting of the sync signal. Okay, so the delay between the starting of the signal and when it is received is called as error. Okay, so we got this as phase out. Okay, so this phase out has to be corrected, right? Then we have a this is known as a positive phase error. So if it is a negative phase error, earlier to this synchronization signal itself, the received bit level has been synced. Okay, so at this level, so now you get an E which is of negative, which we call it as negative phase error. So when it is a negative phase error, your sampling point will be somewhere out of the received bit level. So this much time it is getting delayed, advanced, sorry. So to compensate this phase errors, okay, so uh, the this positive positive phasing, okay, and the negative phasing are adjusted with an SJW bit. Okay, so SJW is a resynchronization bit which is used to stop the synchronization. Even though there is an error, okay, there is no synchronization in the starting, okay, at the ending it makes sure that the synchronization will happen. Okay, so that is with the with providing some SJW. So these are about the positive phase error. When it comes to the negative phase error, the starting itself we are provide the SJW is being provided. So error detection methods, we have CRC error methods, stuffing errors, okay, bit monitoring, form factor, acknowledgement errors. Then analysis. Okay, so let us take a simple example. Okay, so the probability of non-detected fault CAN messages. Suppose say 1 bit error for every each error for each 0.7 seconds will be there, and at the rate of 500 kilobits per second, 8 hours per day continuously if you send for 365 by days per on an year. Okay, and in 8 hours per day with a rate of 5 kilobits per second, there will be a 1 bit error for every 0.7 second. Okay, so this is known to be the probability. So one undetected error in 1000 years if you see. Right, so these are some error frame and error detection methods. Okay, so using error frames like this. So if you see here, so the error recovery time. Okay, the error recovery time will be there in the realistic aspect, which will be equal to error flags plus error delimiter plus intermission feed. So which consumes 23 bits. Right. So this fault containment and transmitter and receiver errors we'll see in the next session. What are the main features and advantages of CAN using over serial protocol? Serial protocol length is very less. Okay, so it is confined to say some 10 meters or 20 meters. That's it. Whereas CAN can extend up to 40 meters. The basic CAN is okay. So now with the invent of this wireless technology, right? So with the help of your Wi-Fi or with the help of your GSM thing, okay. So this can be controlled for a longer distances. And if you try to implement your IoT for your in your CAN protocol in IoT, then the space is uh, unlimited. Okay, so that's the main advantages of CAN, and it is at the higher data rates. So now, what are the main features and advantages of using CAN over serial protocols? So these are the advantages and these are the main features what we have. Right. So any other doubts from your end? You can't simulate as CAN communication for testing. Okay, so all are licensed ones only, and it will be industry designated. The tools of CAN cannot be implemented. To some extent, you can use your NS simulator, okay, network simulator, to for doing that. We can get the features of CAN, but it doesn't mean that you can whatever the simulation you are doing in there will adapt to that. Okay, so they all are industry standard only, all the CAN protocols. There is no CAN communication simulation tools for doing the testing. It is industry because every time it is adaptable and ad hoc depending upon how the components are connected. That will depend.
Hello, sir.
Yes, sir.
Sir, actually, embedded system is a very vast syllabus. Okay.
Yes, yes, yes.
Sir, please explain if students want to work on real-time projects using
Okay.
embedded systems or microcontroller, then what are the basic steps if he knows the basic programmings of 8051
Hmm.
microcontroller?
Sir,
Then,
if
sir, what are
just
the other steps so that they can
yeah,
start the projects on embedded system?
yeah. So if you are good at 8051 programming or ARM programming, you can start working from Arduino projects itself. Arduino boards you can take and you can start working on.
Hmm.
Okay, and Raspberry Pi to some extent. Okay, and
Hmm.
ESP Node 32. So actually, so one session I'm going to take how to use this Arduino boards, Raspberry Pis, and ESP32 boards. Simulation I'm going to
Hmm.
show you, right? But the programming is at the end we have can write it in ALP or embedded C.
Hmm.
So
Okay.
some simulations
Means
I'm going to do in the next session.
y-
Okay, so that they can
hmm.
have an idea how to do those projects. Simple projects only.
Maybe from YouTube also,
Okay.
if you can, if the students can browse, they can get it. Okay, but how?
But sir, if they want to, sir, if they want to work on real time projects on microcontroller, like actually, sir, if you search over the internet, thousand or more than thousand number of projects may come at a glance.
Yes, yes,
So actually, and some predefined programs are also given there, so that they can take the program code and paste them in the Arduino,
okay,
and they can run and build the prototype. Okay.
yeah,
Actually, sir, I am not asking in this field. I am asking for that if they want to create something which
yes.
will be novel and innovative.
Yeah,
So
definitely, sir.
then,
Okay. See,
yes.
just for an example, I will just take an example, simple. So we have an LED in our homes, right? So nowadays all are LED
Mm.
lights, right? So what we are doing is we are giving 230 volts AC. Okay. So this 230 volts AC is directly converted to some 5 volts or 6 volts DC. Okay. So
Mm.
there will be a rectifier circuit within the LED bulb, which will control the
Mm.
illumination of the, which will give 5 volts directly to the LEDs. Okay. So when this circuit fails, the LED bulb is going to fail. Am I right? So it
Yes, sir.
doesn't mean, yeah. So it doesn't mean that the LEDs have failed. It is LEDs are not failed actually there. The circuit, the rectifier circuit or the regulator circuit that is inside, that was failed. Now in this case, we can automate that. Okay. Like we can change the illumination of the LED by using some microcontroller. Okay. For that, we can use a simple ESP node or we can use an Arduino board. Okay. So this, instead of uh, directly giving this 5 volts to the LEDs, instead of that, we can give through an Arduino board, which consists of a microcontroller. You can control the illumination just by putting a potentiometer at the knob of the LED switch. Okay, so if you want to go further, based on the light intensity of the room, the illumination can change, the illumination of the LED can be changed. So like this real-time aspects we can take and we can control it. But only the thing is
Oh,
when we implement in the real time, okay, the sensors will not work actually. The sensors will work for
mm.
the prototypes, whatever the students uses for the projects will work on 5 volts only. Whereas in real time, you don't require 5 volts, you require 24 volts. And this 24 volts can be done with the help of the Arduino boards, not Arduino boards, can be controlled with Arduino boards. They will not provide actual, they can control. So
Okay,
this real
sir.
time
Means
scenario,
making the projects about the students that the Arduino platform, Arduino Uno, Mega,
yes, sir.
or Nano, that are the basic standards.
Okay. Yeah, anything we can take it. So for real time, Arduinos are best. Okay. If you are having any
Real-time
high processing
Arduinos.
in,
Okay.
then you can use Raspberry Pis.
Mm.
And whenever there is some communication, wireless communication, then you can use a board like ESP32.
Okay,
And
sir.
nowadays there's
Thank.
Siemens and Philips. They are coming up with their own boards. Okay, so for academic purpose
Actually,
also they are having it. So you can just go
uh,
ahead with them and get the boards for real time implementation of the project.
yeah, sir. Also, the cost of the boards are also very high.
No, if you go to the Siemens or the Philips, okay, so
Hmm.
academic program, under academic program, you could get at free cost. But the only thing is the
Okay.
problem statements you have to fulfill. That is one way, and
Hmm.
there is
Hmm.
then one NPTEL program where the students can they take up the course called Embedded Systems using ARM. Okay. They are
Hmm.
supplying some TI boards per college, not for individual.
Hmm.
Okay. So there should be a
Hmm.
coordinator who should lead the students. Okay. So if they do it, the boards will be of free of cost. Okay, but they will not give the peripherals. We have to buy the peripherals outside.
Hmm. So,
Both
can you tell me the name of the NPTEL program again?
embedded systems designed using ARM.
Hmm. Okay, sir. Yes, sir.
So, right.
Okay, sir.
Yeah.
Thank you for the information.
Yeah.
Yes, sir.
Right.
So thanks for the day. So tomorrow we'll just come up with this. I will close the CAN protocol, and then we'll start with some other some real Arduino boards, Raspberry Pi boards, or small projects. I'll try to show you. Okay, then we can close it. And the last day, so you can